half of 2 bonding electrons. So 6 plus 1 is 7. Each of these chlorines over here is in a 0 formal charge state. Carbon normally comes with 4 valence electrons. We've got 4 bonds drawn to carbon. It gets half of those of each of those of all of those electrons in the bonds. So half of 8 bonding electrons is 4. Our Lewis structure so it shows the carbon with a 0 formal charge. This structure, note real quick here, has 0 formal charge. Remember, we don't like to have formal charge in a molecule because it actually takes energy to separate positive charge and negative charge from each other, etc. So right off the bat, we should be able to look at this structure and say, wait, that's looking pretty good. Just for the sake of argument, let's look at the others. This chlorine over here, 3 lone pairs, 1 bond, 0 formal charge. Carbon, 4 bonding, 4 bonds, 8 bonding electrons, of which it gets half. That's 4 electrons associated with carbon. It's also in 0 formal charge. Your oxygen normally comes with 6. We've got it associated with 6 lone pair electrons plus half of these 2 bonding electrons. It's actually shown with 7 in this Lewis structure. So this structure shows the oxygen is shown with 7 when it normally comes with 6, and so that oxygen has a -1 formal charge. Chlorine down here normally comes with 7. We've got 2 lone pairs, so that's 4, plus half of the 4 bonding electrons in those 2 bonds. That's 5/6. This chlorine is only shown associated with 6 electrons. If it normally comes with 7, but the Lewis structure suggests it's only associated with 6, then that guy is in a +1 formal charge. So this Lewis structure has a negative formal charge on the oxygen, a positive formal charge on the chlorine. This structure over here has no formal charge anywhere. Chlorine's a pretty electronegative element. It's not as electronegative as oxygen, but it's pretty electronegative. Not a good thing to have a positive formal charge on chlorine, not physically realistic. And we've got that to have this particular kind of an electron distribution on the molecule, you had to take positive charge and negative charge and move them apart. That's high energy. We don't like to do that. So which of these structures is the best? That guy right over here on the left minimizes the formal charge. Okay? All right, so remember that big long-winded thing I told you at the beginning of this lecture about how we can't know just from the equation what the rate mechanism is going to look like because we don't know what the rate limiting step is? Well, problem number 4 right here touches on that. Problem number 4, let's see here. Put this one up on the board. Proceeds through 2 steps. Eraser. Step 1, F2 plus ClO2 goes to FCl2 plus F. Step 2, F plus Cl2 goes to FClO2. ClO2. Now,
Step 1, you missed an oxygen.
it's F2 plus ClO2 goes to FClO. Oh. ClO2 plus F, and then F plus ClO2 goes to FClO2. When you're looking at these kinds of problems, first check to verify that the sum of the steps is equal to the net reaction. So over here in the products, we've got F gets consumed over there, and the sum is that F2 plus 2 ClO2s go on to form 2 FClO2 species. Yeah? Okay. So generically, the generic rate law that we're going to write for this is that the rate is equal to some k forward in the forward direction times the concentration of F2, some coefficient that we don't know yet, times the concentration of ClO2 to some coefficient that we don't know yet. Sorry, there's a piece of information I have to scan this for. One more thing that we need to know to solve this. Okay. All right. So then they tell us this right here in this line. They say that when the concentration of F2 was doubled, the rate of the reaction doubled. Yeah. So if a species is not involved in the rate limiting step at all, you can change its concentration all you want, and the rate of the reaction is not going to change. So when they told us that the rate does in fact increase with the concentration of F2, that suggests that F2 must be in the rate limiting step. Yeah? If it's involved in the rate limiting step, then its concentration is going to affect rate of the reaction. Well, then they go on to ask us which of these mechanisms, or if this mechanism is valid, if this mechanism is true, which step, 1 or 2, is the rate limiting step? Well, what you should be able to identify is that step 2 does not have F2 as a reactant. Step 2 has just single F, single fluorine atoms. Well, it can't be the rate determining step because it doesn't involve F2. Step 1 must be the rate determining step because it's the only step that actually involves F2 as a reactant. And so if you know for a fact that this mechanism is real, or if that's the real mechanism, then that pinpoints step number 1 as the slowest step of the reaction. If we were going to draw this on a reaction diagram, we would draw, I don't know if this thing's endothermic or exothermic, doesn't matter too much. We would draw a really big hill for step 1, because that's going to be the slowest step. Right? So here's step 1. And then we might draw a smaller hill for step 2. And we go on to products. The rate determining step has the largest barrier to reaction. So step 1 would be the rate determining step. It asks us downstairs here about whether or not things are catalysts or intermediates. Definition of an intermediate is that it gets generated in one step and then it gets consumed in a subsequent step. And so you don't, that species doesn't hang out for long in the solution. This F atom that shows up as a product in this step and a reactant in that step, that's your intermediate. catalysts. Catalysts are kind of the inverse of intermediates. Intermediates get generated and then consumed. Catalysts get consumed and then regenerated. There's no catalysts in this reaction. I'll bet you money, though, there ends up being a catalyst in another reaction. Look down here at reaction 5 on the bottom. Oops, where's that guy at? Down here, reaction 5. You see how I minus in step 1 gets consumed, but then in step 2, I minus gets regenerated? You see that? I minus is a catalyst. It doesn't get used up in the reaction. It acts to facilitate the reaction. Somehow it's interacting with the transition state to lower the energy of the transition state, and that makes it easier to get over the reaction barrier. But it doesn't get used up. It's allowed to keep performing its function over and over and over again, which is what makes catalysts so cool. One catalyst will catalyze a million different reactions. So if you were to look at that reaction and talk about what is a catalyst, you would identify I minus as a catalyst. So you need to be able to look at these things. You need to be able to, from rate data and suggested mechanisms, pick out which step in the mechanism is the rate determining step. You need to be able to identify catalysts and intermediates, and I think that's about it. Okay? Number 6, this question number 6 in your practice exam. There's 3 different ways that you can increase the rate of the reaction. Tell us what the ways are. Way number 1, increase concentrations. Concentrations of reacting species go up, collisions go up, rate of reaction goes up. Method number 2, increase the temperature. You increase the temperature, you increase the linear velocity of the molecules in the solution or in the system. Therefore, moving faster, they collide more frequently, but most importantly, their collisions have larger energy transfers. And so at higher temperatures, because the collisions are more energetic, it's much easier to get over any reaction barrier. And so higher temperatures speed up reactions, not simply because they include increased collision frequency, but mostly because they include increased collision energy. Okay? Third way that you can increase the rate of a reaction, add a catalyst. You add a catalyst, you're lowering the transition state where you're providing the reaction with a different path, a lower energy path to get to products. And that will speed up the reaction. Okay. Number 7. 7 says, place the following acids in order from the strongest acid to the weakest acid. And all I give you is a bunch of Kas, the equilibrium constants. Well, for a strong acid, a lot of the species are going to dissociate. You know, something, where's my acid picture? Something that's a strong acid is going to kick off a lot of those protons. If you got a lot of protons, you've got a lot of reactants in the numerator of your equilibrium expression, right? So therefore, you have a very large K value. So your job in ranking these acids is to simply look at the sizes of the Ks. Whichever Ks are largest, those are the strongest acids because they go furthest towards the product side of the expression. Whichever acids have the smallest Ks, those guys are the weakest acids because they don't dissociate very readily at all. So number 8 here, moving forward with acids. It's just basically asking you which one's the acid, which one's the base. You've got an acid and the base on the reactant side of the equation. You've got a conjugate acid and a conjugate base on the product side. So In this guy, HS minus plus H2O goes to H3O plus S2 minus. It's the H that was on that HS minus that gets transferred over to the H2O. So HS minus is the acid, H2O is the base. The base provides the lone pair for the proton to dock onto. Over here in the reverse reaction, it's an equilibrium reaction, so we have forward and reverse directions. In the reverse direction, the lone pair that the proton is going to land on is on the S2 minus. And so the S2 minus is your conjugate base. The thing that donates the proton is the hydronium ion, H3O plus. So that's your conjugate acid. That proton on the H3O plus will dock onto a lone pair of electrons on the S2 minus. It'll generate water in HS minus. So you need to be able to look at these equilibrium expressions and identify acid, conjugate acid base, conjugate acid, conjugate base. Here's some mind benders. Number 9. They give you an equilibrium expression. They say you got HOCl plus H2O is going to equilibrium with H3O plus OCl minus. This is just an acid-base equilibrium. They ask you to write the expression for Ka. You guys can do that. They ask you to identify the acid and the base. You guys can do that. Then they ask you, if you add extra OCl minus to this reaction, will the amount of H3O plus increase or decrease, and why? So here's the story. You're putting more of the products of the reaction into solution. Your one particular product, OCl minus, you're increasing its concentration. What that does is it speeds up the reverse reaction rate relative to the forward reaction rate. Yeah? You speed up the reverse reaction rate relative to the forward reaction rate, you're going to push the thing toward the reaction towards the left, towards the top, or towards the reactants. If you push it towards the left, towards the reactants, products get consumed. What they asked you was, how does the concentration of H3O plus change when you add OCl minus? Well, if you add OCl minus, you increase the rate of the reaction for which H3O plus is a reactant. Therefore, H3O plus is going to get consumed. So the answer to this question is, an increase in OCl minus concentration is going to lead to an eventual decrease in the H3O plus concentration. Now, that logic, pretty easy to deal with in number 9. Look down here in number 10, or no, sorry, not even number 10, we'll look at number 11. Number 10 just talks about a different kind of an equilibrium where they say that delta H is greater than 0. Well, for that, we have to start looking at the temperature effects of equilibrium. We said that an increase in temperature is going to favor whatever species, reactants, or products that are higher in energy. So that's all you need to know for this one, is that a change in temperature is going to need to favor the higher energy species. But back down here to 11. 11 is just an extension of the kind of logic that we looked at 9. Okay. Except what we've got going on here in 11 is that we've got 3 interrelated equilibrium expressions. And what they ask you is, if you add Fe3 plus aqueous to this, how is it going to affect Cu2 plus concentration? Fe3 plus is a reactant in the bottom reaction. Cu2 plus is a reactant in the top reaction. Your job is going to be able to look at those 3 reactions and see how those interrelated equilibria work. This one hurts my brain. I'm going to try to do it real quick for you. I'm not going to write it down and talk about it, but I might mess this one up. We had Fe3 plus. We increased the rate of this forward reaction on the bottom. Yeah? Well, that forward reaction requires the consumption of OH minus. And so by increasing the amount of Fe3 plus and driving that reaction forward, we decrease the amount of OH minus. Yeah? OH minus goes down. Well, OH minus is on the product side of this equilibrium expression. And so if we decrease the amount of OH minus, we drive that reaction to the right. Yeah? If we drive this reaction to the right, we consume NH3, correct? Because NH3 is a reactant in that reaction. And so NH3 gets consumed. But NH3 is a reactant in the forward reaction of the top reaction. And so by decreasing the NH3, we slow down the forward rate of this reaction relative to the reverse rate. So NH3 decreases, this guy drives backwards. Well, guess what? When this top reaction drives backwards, you increase the amount of CO2 plus. And so, the answer to this question is, if you add Fe3 plus to the system, you're going to increase the amount of CO2 plus. That was mental gymnastics. You're not going to see anything that hard on an exam, but I encourage you to please take a real hard look at that problem over the weekend. If you can do that problem inside and out, you won't have any trouble with anything that we look at on the exam. Okay. 12 down here. What's 12 say? It says we got these 3 different equilibria, place them in order from the most water soluble to the least water soluble. Well, the size of KSP tells you which one's the most soluble. Whichever one has the largest KSP is going to have the largest concentration of those dissolved ionic species. So all you got to do is look at these 3 numbers, figure out which one of them is biggest, and whichever one's biggest, that belongs to the most soluble of those species. All right. Problem 13 down here. This is just going to be one of those delta H calculations that we did in the last exam. But at the end of the calculation, you're going to know whether or not this thing's endothermic or exothermic, right? And they ask you, they say, are you going to have to heat the system or cool the system to increase the solubility of calcium carbonate? Well, you got to figure out if it's endothermic or exothermic. You got to, based on whether it's endothermic or exothermic, you're going to be able to determine which of those species are highest in energy. And you know that an increase in temperature is going to favor the highest energy species. It's a really weird thing, but I just want to reiterate that when you increase temperature on a substance or a system, you're asking the molecules and the atoms to carry more energy. And they do this by increasing their velocities, their vibrational, rotational, and translational kinetic energies, but they also do it by shifting the distribution of species towards the more energetic species. So that's the whole deal with the endothermic, exothermic equilibrium. Increased temperature in favor the highest energy species, whether it's reactants or products. Go in there, pick that thing apart, figure out whether it's the reactants or the products that are higher in energy, and then you'll be able to predict which direction the reaction will shift when you change temperature. And the way that you're taught to think of this in Gen Chem classes is you think of heat as one of the products or reactants in a reaction. So for an exothermic reaction, products go to reactants plus heat that's released. And so if you increase the heat, you're increasing one of the reactants for the reverse direction. So if you increase temperature, the reaction shifts that way. Yeah? For an endothermic system, we think of heat as products or reactants products. We think of heat as a reactant in the forward direction, and so it's reactants plus heat goes to products. Therefore, if you increase the temperature, you drive the reaction towards products. Does that make sense? All right, go home, practice this stuff. I'll be in lab today. I'll be giving exams back in lab, and a lot of people did really good. You know what that means? It means you can really afford to screw up on the final. All right.
Do we have lab?
Today?
Yeah.
Yeah.
Oh, you said go home. Yeah.
Well, no, I mean, for the next 40 minutes.
Oh,